Okay, just a little bit more of evolution to make sure that we're on the same page here. And right off the bat, a few different terms. We can talk about what's called a population, means different things in different sciences, but for biology and for paleontology, we talk about groups of interbreeding individuals. And then we can define a species as all of those populations whose members can interbreed if they come into close contact with one another. This works for dinosaur species as well as all modern species. So Tyrannosaurus rex can change or evolve over time and give rise to new species. But if you're looking at it at any one particular time, you can say, here's the population of Montana T-Rexes. And maybe over the course of their lifetime, they're never going to be able to see a population of Texas T-Rexes. But if you were to magically take one male from one area and one female from another and put them together, they could still potentially interbreed. We see this today with all kinds of species out here. So, right now we're about to have a big snowstorm move in, and I'm feeding all the cardinals in my yard. And, there's cardinals, beautiful red bird, the males are beautiful red cardinals. There are populations here. Where my parents used to live in Texas, there's also cardinals, and Texas cardinals are a different population. They don't see each other at all, but if, again, I took a male cardinal from Wisconsin and took him down to Texas, he would be able to successfully interbreed. So if you then take all of these different populations, they're isolated by distance and all kinds of other things, but if you put them all together, sort of circumscribe all of them, that is the species. Now, we want to talk about making new species. Remember, I said that if natural selection operates long enough, if it is going to make natural, sort of change things over time, then you can have different populations going in different directions. You can have population in one area being naturally selected for retention of fat to sort of stay warm in cold areas, but you can have a population in another area that is getting progressively hotter and drier to have less fat or a less percentage of fat cells. And so populations can diverge to the point, again, over millions and millions of years, where suddenly you would not be able to take a male from one area and put him together with a female from another area, and the interbreeding would not work. At that point, we say that speciation has occurred. And it's a very, very detailed subject, and there's many different ways to make a species, speciation. But the primary one is what we call allopatric speciation. And here I've got a cartoon of beetles. These are little beetles, you can see them. And you have one area, and every little beetle represents a different population. And maybe the whole size of this first oval is, 10,000 square miles, 1,000 miles by 100 miles, something like that. And you see you've got green beetles, brown beetles, tan beetles, golden beetles, all of these things, and they can potentially interbreed and mix. But over time, let's say a giant river system develops. In geologic time, this happens all the time. And these beetles, which can't fly, they can just crawl. Suddenly, the beetles to the north of the river are isolated from the beetles to the south of the river. Let's say the area north of the river is progressively more moist. There's more moisture, therefore there's more green plants, more green plant cover. The beetles, which don't want to be eaten by the birds and rodents or whatever, there's a natural selection for greenish color, for refuge, for hiding from things. The beetles to the south of the river are progressively in an environment that is hotter and drier. There's less plants, there's more exposure of raw rock or sand surfaces, so there's selection more for brownish colors, where they would be hidden there by sort of just sitting on brown sand. The brown beetle isn't seen. If that operates long enough, then even if someday maybe this river system switches and changes, it's gone, if these two things have diverged enough, long enough, then they can be separate, and we would say that natural selection through allopatric speciation has caused or created this sort of separation into two different species. Why is this important? Because you need barriers to do this. And barriers in the geologic sense are things like big mountain ranges, the opening of ocean basins, the giant river systems that I talked about before. Geology is doing this all the time through processes called plate tectonics. I'm not going to talk about it in great detail here in this class, but it's mentioned a little bit in the book, and you can look it up online if you want. But suffice it to say that geology creates barriers. Barriers then help create or move forward allopatric speciation. Look at the cartoon over here. Let's say you've got a big system. This is the entire sort of ancient continent of North America, and you've got these different populations, again represented by a single icon here. But let's say you develop mountainous areas in the east and in the west. Let's say the maximum height these birds can fly is just 5,000 feet. As soon as geology has built mountains higher than 5,000 feet, these populations are isolated. And suddenly, these isolated populations may or may not undergo natural selection for different features, such that if in the future then when these barriers are removed, there will not be interbreeding between the two. And so you can take a single species with these many different populations, but if you isolate a population, here we call it a peripheral isolate, natural selection can trend this off towards being a new species. Again, this is just the shortest, briefest introduction to this whole notion of evolution, but I wanted you to see this or think about this in terms of dinosaurs. So, plate tectonics is going to create all kinds of barriers and split things up. Principally, it's this. At the start of the dinosaur era, we had one big giant world continent, Pangaea. So we had one ocean. There was no Atlantic Ocean, no Pacific Ocean, none of that. There was no North America, Europe, Asia. There was one continent, Pangaea, and one big ocean, Panthalassa. And it started splitting and separating and creating the world we know. So that dinosaurs that used to be able to walk, let's say, or interbreed potentially from North America into Europe, or the places that become that, get separated and by this ever-growing, ever larger and larger creation of the Atlantic Ocean. So geology is responsible for the isolation of these populations by barriers. And so it's what makes these it's what is creating these new and different species over time for dinosaurs, over the almost 200 million years that dinosaurs exist. A few other things to think about in terms of geologic aspects of evolution. Adaptive radiations. Adaptive radiations are these short time intervals in geologic terms where lots and lots of species and different kinds of things are created. And what you're looking at here is the evolutionary branching, the adaptive radiation of mammals over time. So I know this is a complex diagram, but bear with me. The bottom part is the Mesozoic. So Triassic, Jurassic, Cretaceous. You can see it here along the left side. This is the time of the dinosaurs. But there are very, very small little mammals that existed then. Dinosaurs go extinct at that red line, 65 million years ago. Suddenly the world isn't filled with these giant beasts gobbling up all the resources in space. And so these little mammals that barely existed when dinosaurs were there suddenly can begin to thrive. And the rest of this diagram, as you go up, again, superpositionally, this is going through time from 65 million to 45 million, 35, 25, and we live up here at the top. That's today. And these are all the mammals of today. There's horses, rhinos, cats, dogs, elephants, anteaters, you name it. They're all living here today. So that's what the biologist sees. The biologist sees all the variety of mammals that exist today. But they have a geologic history going back to well into the dinosaur times. And during dinosaur time period, below this line again, they existed, but ecologically they were on the fringes. As soon as dinosaurs were removed, boom, natural selection through adaptive or through allopatric speciation takes off. 65 million years of time gets us all of our beautiful mammals today. Same type of thing works for dinosaurs. What else can we document in a geological context? Extinction. We also talk about the last organism to go. We know that there are no more T-Rexes existing on planet Earth today. The Tyrannosaurus Rex lived for many millions of years, and then it went extinct. That's extinction. Again, biologists, we are 65 million years away from the last T-Rex that lived on planet Earth. Biologists, there's no way they could study it unless they went to the rock record and paleontologists and learned about them from there. And that's why paleontology is the quintessential interdisciplinary science. It has to sit on the fence and be right in the middle between biology and geology. So paleontologists, it's as if they have to learn twice as much material as other scientists, because they have to be able to speak biology. They also have to be able to speak geology and then translate back and forth for the two different groups. A little sideline for me. And then finally, we need to talk about mass extinctions. Now, mass extinction is just, it's not like the last T-Rex, the last Stegosaurus. It's when many, many, many things go extinct. And this can happen for a whole bunch of things. You can have climate change, you can have a blast of gamma rays from outer space, an asteroid hits the Earth, oceanographic change, all these things. Suffice it to say, and we'll talk about this at the end of the course, there's evolution during normal good times, which is going to progressively get us bigger and badder dinosaurs. But then there are these time periods we call mass extinctions where all bets are off. And then in fact, it's bad to be big and you're more likely to go extinct. And that's the story of the dinosaurs right here. In this diagram right here, the width of this little weird red diagram is sort of the number of species. And then on the y-axis, or the vertical axis here, this is time. And remember, Mesozoic is the era the dinosaurs lived. We had, at the start of the Mesozoic era, we had a small number of families. And then as time went by, you get more and more and more families. They get bigger and bigger, but then at the end of the Mesozoic, and there's that 65 million year line, dinosaurs go extinct. But we have mammals that survive through. Again,